This is 6.1.2, simple harmonic motion. So we're going to start this lesson by first giving you the definition of simple harmonic motion. You must memorize this definition because it's what underpins all of simple harmonic motion. Later on, after the notes are done, I'll do a demonstration, which you won't see on YouTube, but it will be set up in real life. So for those of you who are watching on YouTube, you'll probably just want to go and look at a simple pendulum. So simple harmonic motion, or SHM for short, is a periodic motion, which means it repeats, in which acceleration is proportional to the displacement and in the opposite direction to it. Put a box around that. So let's look at an example of what this looks like. So if we have two pendulums set up, where the dotted line represents the central axis, if we have one pendulum that's displaced this far out, its displacement is to the right, and we call that x. Now, if we have a second pendulum, which is also displaced, or let's displace this one the opposite way, to the left, and we'll also make its displacement much smaller. So we'll call that x. Now, comparing the two pendulums, the first pendulum I drew has a larger displacement. So it will also have a larger acceleration because they're proportional. Acceleration is proportional to displacement. But in the first example, the displacement is towards the right, so acceleration must be towards the left, so it's in the opposite direction. And in the case of the second one, it's going to have a smaller acceleration, but it's going to be pointing towards the right. So now let's write that mathematically. With the defining equation. So we start with acceleration is proportional to displacement. So A is proportional to displacement. We typically don't like proportionality symbols, so we want to get rid of them. And we get rid of them by putting a constant of proportionality in there. So A is equal to some constant times by x. But we're also going to remember the opposite direction. So if we have an opposite direction, we're also going to have a minus sign. Now, by doing a bunch of maths, you can derive it. But instead of deriving, I'm going to give you the equation. So this gives us acceleration is equal to minus omega squared x. Put a box around that. And if we graph acceleration with displacement, we get a negative straight line where the gradient gives us minus omega squared. Okay, start a new page. So now we'll do displacement and time. So let's imagine we have a pendulum, and we take this pendulum, we displace it by a certain amount. The amount that we displace it by before we let it go is its maximum displacement. It can never swing more than that. So if we have here its maximum displacement, this is called A, the amplitude. Yeah? So amplitude, which is also the maximum displacement. And when we let it go, we start the clock at that position. So we start the time here, t equals to 0. That pendulum then swings back and forth, back and forth, back and forth. An equation that describes its displacement is given by x is equal to a cos omega t. So now what I want to do is I want to graph this. So we put t on the x-axis. We put its displacement on the y-axis. We're going to draw a cosine graph. And this value here is the amplitude. And this value here is the negative amplitude. Now, in real life, let's look at the pendulum. So I'm going to do a dotted line there, a dotted line there. So I'm only doing it in points of interest, which are the maximas, the zeros, and the minimas. These are our points of interest. And everything else in between, you can fill that in with your imagination. Okay? So I've roughly got these dotted lines lined up with the pendulum's location. So at the beginning, we've got maximum positive displacement, which means the pendulum is all the way to the right. Then we've got here 0 displacement. So the pendulum is in the middle. Then we've got maximum negative displacement. So the pendulum is there. Then it's 0 again, so it's in the middle. Then it's to the right again. Then it's in the middle. Then it's to the left. Then it's to the middle. And then our graph finally ends when it's on the right. So these are the pendulum locations as we follow that graph. So that's what we started with. Now, if we were to start the time of our pendulum when it's moving through the center, then instead of a cosine graph, we start with a sine graph. Yeah, but most of the time it makes more sense to start the clock for the pendulum when it's at its maximum displacement. So now, we're going to look at velocity. And time. So let's recall the definition of velocity. The rate of change of displacement. So velocity is the rate of change of displacement, which basically means v is equal to dx dt. So let's go back to our original equation. A cos omega t. So we want to find velocity. We're going to do v is equal to d by dt of A cos omega t now. A is just a constant, so it comes out. When you differentiate cos, you get minus sine. So we've got minus A sine omega t. But inside of the cos, we have a function of time, omega t. So we have to apply chain rule and differentiate the inside as well. So omega t differentiates to omega, and we bring that and multiply it to the outside. So on the outside, we now have minus A omega sine omega t. Now, we can actually relate this equation. We can relate this equation to the displacement by doing a bit of maths on it. So relating v and x. So let's start by squaring this function. So if we square it, we get v squared equals to a squared omega squared sine squared omega t Now, we use our trig identities. Sine squared is equal to 1 minus cos squared. So using trig identity, sine squared x plus cos squared x always equals to 1. So we're going to do cos squared minus 1 minus cos squared. So we've got v squared equals to a squared omega squared multiplied into 1 minus cos squared omega t. Now let's multiply these out. So we've got v squared equals to a squared omega squared minus a squared omega squared cos squared omega t. Now this second term, a squared omega squared cos omega t, looks fairly similar to something that we know, which is up here. So let's write it on the side here. If x equals to a cos omega t, then x squared equals to a squared cos omega t. So we've got a squared cos squared omega t. We just have the extra omega squared. So a squared cos squared omega t is just x squared. So this now, v squared equals to a squared omega squared minus omega squared x squared. We can factorize the omega out. So v squared equals to omega squared a squared minus x squared, square root the whole thing. So v equals to square root of omega squared is just omega, square root of a squared minus x squared. Put a box around that because you need to know it. So now we've related velocity to displacement. Now from this equation, we can figure out the maximum velocity. So maximum velocity happens at 2 points. Number one, we can find it by looking at the trig function, which is minus a omega sine omega t. So the amplitude is constant, a, omega is constant for that system. So the only thing in that function that changes is the sign. So what's the range of sine? Well, it's 1 to minus 1. So its maximum magnitude of sine or cosine is just 1. Because we don't really care about negatives here, we just want to know about the magnitude. Its maximum magnitude is 1. So the maximum velocity happens when the sine is equal to 1. So max velocity when sine omega t is equal to plus or minus 1, or when displacement equals to 1. Sorry, displacement is equal to 0, not 1. Now let's think about that for a moment. If the sine function is a maximum, at the same point the cosine function is 0, because they're pi over 2 out of phase, or 90 degrees out of phase. So when sine is maximum, cosine is 0. And we can see it from this equation as well, is if x is 0, then we're not taking anything away. If x is anything other than 0, whether it's positive or negative, we're taking something away, because the negative gets squared, it becomes positive, and then we're taking away the squared of x. So we maximize the function when x is non-zero, so when x is 0, and we start to minimize it when x is anything other than 0. So let's write them down. V equals to minus a omega sine omega t, or v equals to omega root a squared minus x squared. So set to plus or minus 1, and here we're going to set x to 0. And in either case, we end up with the same thing. V equals to omega square root of a squared. So it's v equals to omega a. And over here, you got minus a omega, or omega a, whichever you prefer. But sine can be plus or minus 1. So that sine can also be plus or minus, right, depending on which way it's moving. So in either case, v equals to, and even with this case, this is just giving us a magnitude. If we wanted the direction, it's also got plus or minus. So v equals to plus or minus a omega, or omega a. So they both give us the same thing. And so this occurs when our pendulum is in this position, x equals to 0, or for a spring system, where our mass is in the equilibrium position. Now, since this is the maximum velocity, we're going to label it as v naught, just so we can differentiate it with the changing velocity v, which is a variable. Now, start a new page. Acceleration and time. So acceleration is just the rate of change of velocity. So a equals to dv dt. So now let's differentiate. So a equals to d by dt of minus a omega sine omega t. So again, a and omega are constants. So the minus a omega, we put that to the side. When you differentiate sine, you get cos, and then we apply chain rule. Omega t becomes omega. Multiply that to the outside. So we get a equals to minus a omega. And then remembering the omega that just came out of the chain rule, so it's omega squared cos omega t. Put a box around that. And then I think to myself, hold on a minute. That a cos omega t, that looks awfully familiar. Oh, that's just displacement. So a equals to minus omega squared x. And we got that first equation. So then we think, how can we get maximum acceleration? Well, you could do this in several ways. Think about the definition. If acceleration is proportional to displacement, then maximum acceleration happens when you have maximum displacement. Or you could say that cos needs to be set to 1 or minus 1. Because that cos set to minus 1 or minus 1, we get a equals to plus or minus a omega squared. And if it's a omega squared, but a is equal to minus omega squared x, then that means x becomes the amplitude. So the largest acceleration happens when your pendulum or your spring is at its maximum displacement. So we set cos omega t to plus or minus 1, or max value of x is a. Therefore, our maximum acceleration is plus or minus omega squared a. Put a box around that. Right, finally we'll draw some pendulums and look at how each of its properties change depending on its phase, depending on its current phase in its oscillation. So in the center we draw a pendulum in the center. On the right hand side we draw a pendulum at max displacement to the right, and on the left we draw max displacement to the left. So in each case we'll have displacement, velocity, acceleration, kinetic energy and potential energy. So in this position all the way on the left, it's got maximum negative displacement. So I'll write that as negative max. Velocity is 0 because when it reaches maximum displacement it stops before turning around, similar to like how a projectile stops when it reaches the top before turning around. Its acceleration is going to be maximum but towards the right, so it's positive max. Now if it's not moving, it's got 0 kinetic energy, which means it must have maximum potential energy. Then in the center, we do the same thing, x, v, a, ek, ep. So in the center, it has no displacement, so that's 0. In the center, its velocity, depending on which way it was coming from, if it was coming from the left, then it's going to have positive velocity. If it was coming from the right, it's going to have negative velocity. So it's plus or minus max. In the center, there is no acceleration, because if you got a equals to minus omega squared x, in the center, x is 0. So omega squared times 0 is 0, so acceleration is 0 in the center. Ek is maximum because it's got maximum velocity, and Ep is 0. And then finally, on the right hand side, we've got x, v, a, ek, and ep. And this is a symmetric system. So it's going to be the same as the left-hand side, but all the values will be flipped over. So negatives become positives, positives become negatives. So x is going to be plus max, v is still 0, a is minus max, ek is 0, and ep is max. And then finally, we just want to compare the three graphs and how they look. So if we have here x, t, v, t, and a, t. So x was a cosine graph, Then V was a negative sine graph. And then A was a negative cosine graph. So this is how they compare. And that's the end of 6.1.2.